Well, hello and welcome to Untangle, where complex topics meet clarity. Today, we're exploring the backbone of modern life: electricity generation, distribution, and transmission. From power plants to household outlets, we'll be tracing the journey of electricity and unpacking the intricacies of the systems that keep our world running. I am Blessing Dagin, and joining me today is engineer Olajide Adebayo, an expert in the field who will be helping us untangle the wires and get to the heart of the matter. Thank you so much for joining us, engineer.
Same here, it's good to be back.
Actually, you were here the last time, just not with me.
Yep.
All right, so let's go straight into the issue of the day, talking about electricity generation, distribution, and transmission. Let's start from the basis. Can you explain what this means? What is the difference between electricity generation, distribution, and transmission?
All right. All right, I'll try to use, let me say, simpler terms.
Yeah.
And also what everybody can relate with. Mm-hmm. So electricity generation, the value chain starts from generation. Okay. So electricity generation is, let me use pure water. So when you have a pure water factory, okay, the pure water factory generates the water, either in sachet or in bottle.
Okay.
The transmission is that truck that moves it from the factory to the store where you buy from. Okay. The distribution is that store, supermarket, whatever it is, that sells in bits to everybody. So electricity generation typically is at generation level. Electricity is being generated mostly at 12 kilovolts. Okay. Then it's being stepped up using a step-up transformer to 330 kilovolts. At transmission step it down from 330 to 132, then from 132 further to 33 kV. So at distribution picks it up at 33 kilovolts, okay, and further step it down to 230 volts. Now, the essence of all this step up, step down.
I was going to ask about that.
The essence of step up, step down is at the generation level. Of course, you know, at the distribution level, later I have 11 kilovolts and 33 kilovolts. So if we are generating at 12 kilovolts, common sense, why don't we just use it that way? You can't transmit 12 kilovolts. By the time you transmit 12 kilovolts and it gets to the customer end, the voltage will have depleted. Okay. And what powers your home, what makes it your light bulb to not, let me use the common term, low current. Mm-hmm. Yeah, what makes your light bulb to be not to be low current is when it has the sufficient voltage. Okay. So you have to step up so that you can transmit. We have our power generation mostly in the south today. Okay. We have, I think, about 7 in the north, about 21 in the south. The bulk of the energy generated is from the south. Now, that bulk of energy is being transmitted to the entire country. So by the time you transmit 12 kilovolts, it will be lost before you even get to the north central. Oh. So for it to be able to get to the north, northwest, northeast, and still be sufficient for usage, then you have to step it up to 330. At that 330, it can travel longer distance. Now, when it gets to where it will be used, then all the step down will happen. Okay. Because your device at home cannot use high voltage. Okay. And also high voltage cannot, it's not safe, right? That's why there is a standard in terms of distance between home and power lines, just because all those high voltage power lines has an electromagnetic field around it. Okay. If you go closer to a level, you don't need to touch the wire before you get electrocuted. Right? That's why we cannot use high voltage in our homes. So it has to be stepped down to usable voltage that can pass through all the tiny wires in your house, that can be used through all those small appliances, and there won't be explosion in your home. So typically that's what happens, and that's why all the step up, step down happens.
Oh, well, this is great and very enlightening already. But then I have a question as a typical Nigerian. All right. If there are processes to all of this, I mean, you just broke it down to the simplest forms, and I totally understand. But then if there are processes to all of this, why do we still have low voltage and sometimes high in our homes?
All right. So in terms of high voltage and low voltage, typically it's because of faults. Right. So there are areas where we still have the electricity travel for distance.
Okay.
At some distribution companies has feeders, we call them feeders, those lines that travel as much as 50 kilometers, even more than. Typically, the transformer or the last transformer on such line will have a reduced voltage. The voltage at the start will not be what is at the end. In between the injection station is where the transformation happens, and where customer will use. A lot will have happened. A lot of losses would have happened on the way. So when it now gets to the home, then it got depleted. Another reason why you could have low voltage in your house is if there is a fault at the transformer end. So we have three phases.
Okay.
So when you look at the high tension line, what we call high tension line, those lines that are vertical, there are 3, 1, 2, 3. It's red, yellow, blue. There are phases. There is a reason why it's like that. So when you get to the transformer, it comes as 3 phases also. When it's leaving the transformer, it comes as 3 phase and neutral. Now, if you have a neutral problem at the transformer, there will be a voltage problem at the home. If you have one of the phases disconnected between the transformer and the line, you will have a low voltage at home. If you personally, your wire between the pole and your house has a fault, you could also have low voltage at home. So typically what causes low voltage is fault. It's not meant to be.
Okay.
So it could be fault from any level.
From either of the 3.
Either from the transmission. It could be a fault from the transmission or the distribution or even your own wire to your pole.
Okay.
So that's what causes low voltage.
So what about high?
The same thing.
Same thing. So
because it's voltage, how do I put it? Voltage goes, you can't have a straight line voltage. That's why we call it alternating current. Alternating current goes this way, right? So the voltage of such alternating current also, it can't be straight line. So if it's 230, you can't have 230. That's why in the grid code and distribution code, we have standards. In the standards, there are thresholds. So if you set the standard for our voltage at distribution level today is 33 and 11 kilovolts. Now, that 11 kilovolt has a threshold, upper threshold and lower threshold. So it's expected that your voltage should not go beyond, let's say, that would be 10.4 something. Then it must not go above 11 points. So there is that threshold for both the voltage at every phase, at every value chain. So it could go higher. It could go higher because if there is a fault, the voltage will not be going down. It will just be going
high and low.
Higher and low, higher and low. So depending on, there's a lot to it anyway, but that's just how I can explain it. Fault leads to either going up or coming down.
Oh wow, I feel like a pro right now. I can literally understand why sometimes, the light is high or the light is too low. You can't pick up some home appliances. Well, that's quite interesting. But then let me take you back to the first thing, the generation.
Yeah.
Can you just give us some sources? How is this electricity generated?
All right. In Nigeria today, we have typically 2 sources on the grid.
Okay.
We have we are generating using water. That's the hydropower plant.
Okay.
Or we are generating using gas. So that's why we have most of our generating plants in the south because of the gas availability in the south. The pipeline and all that is in the south. Then you have typically the hydro in the north central towards Niger State because of the River Niger, and it's easy to dam and all that.
Yeah.
So typically when you generate electricity, you are converting from one form of energy to another, to electrical energy. So you are converting for gas, you are converting from a chemical energy to an electrical energy. So a gas power plant uses gas, just like your home, where you pour petrol in your generator and you start your generator and then you see electricity out. You don't see the petrol.
Yeah.
So the petrol runs the motor. There is a motor that rolls. In the rolling, that's where electricity is being generated, because it's meant to roll to create what we call electromagnetic field. That electromagnetic field is what is being tapped with wire, then it becomes an electricity that you can use. The same thing with hydro. The only difference in any form of electricity generation today is what drives that motor. Okay. For hydro, it is water that drives the turbine. We call it turbine. It's water that drives the hydro turbines. So the force of the water, that's why it will be damped for it to have a force. So that force, and then the step where the turbine will be and where the dam height will be must be high enough to produce the required force to turn the turbine under the water. So once you turn the turbine will be creating electromagnetic field and it will be tapped as electricity. The same thing with gas. Gas will fire the machine, turn it. Then the gas is being used to generate steam. Then the steam is being used to turn the turbine. But at the end of the day, there must be a mechanical force being generated, which is to move a particular turbine.
The turbine.
Yes.
Okay.
Then from there, it will generate a field that is being tapped or converted to electricity, and then you get it to use at home. So for Nigeria today on the grid, we have just the gas and the hydro. But in our homes, you have solar. So the solar PV trapped your sun, converts it to voltage. Then your inverter converts that voltage. That voltage is a direct current voltage. So it converts that DC, 12 DC, to 230 volts that you can use in your home.
At home.
So, and then there is wind also. Wind can also be used because the idea is just there should be a turning. For wind also, the wind turns the wind turbine. When the wind turbine is being turned, the machine is rotating and it will produce an electromagnetic field and then it will be tapped. There are other sources like what's it called? Biogas. Biogas, the idea is also it generates gas. The gas is being used to turn a turbine. There is coal. Coal also, it generates, coal will burn in a boiler. Then that will heat up a water and the steam will use to turn the turbine. So at the end of the day, there must be a turning, whatever you are using as your source. It must turn a machine for it to generate electricity.
Oh, quite interesting. That explains why some areas, for example, when you talked about the south and then the north central having water and then they're using what they have there, it explains why some places have more supply than other places, right? Because of maybe the travel distance?
So we operate a radial system in Nigeria in terms of transmission. So wherever you are generating, we still put it more like we're putting it in one pot. Then we'll now send out to everybody. So it's not a system where what was generated in the south is only used in the south. No.
Okay.
Wherever you're generating in Nigeria today, we are operating a centralized system. So that's why if there is a fault in the north, the entire country can go into dark. If there is a fault in the south, the entire country, because whatever happens at this station, if it's not quickly mitigated against, it can throw the entire country into the dark because we are all connected in a way.
Wow, interesting. So now you mentioned quite a few sources. You mentioned water, you even mentioned coal, gas, and all of that.
Yeah.
Now, does the source of the electricity affect or impact the kind of supply that is being gotten?
No. So I would say no. The only difference is the technology that is being used. So because that's why there are standards. If you generate with water, we must end or meet at the same place. Somebody that is generating with gas will meet us. And that's why whatever voltage you generate at is expected that you step it up to 330. So once you step it up to 330, it becomes the same. The grid will not see it as this is coming from water. This is coming from. The only difference is the hydro guy might be able to start his turbine faster, or the gas guy might be able to start his turbine faster. That's just the difference. And then when the source is being affected, then if we are in drought, definitely our hydropower stations will not generate as much as they should because there is not enough water in the waterways. If there is shortage of gas or there is a vandalism on the pipeline and the gas could not get to the power generation, then they won't be able to generate. But when it comes to the quality of what's being generated, it's the same. That's why there are standards, because machines are made to, wherever you are generating it from, to bring that standard at the end of the day. So that voltage, because what's the standard is about is more about voltage and frequency. So that voltage and frequency must be maintained.
Oh, very, very interesting, I must say. All right, so now let's talk about transmission. I think we've dealt extensively well with generation. Let's talk about transmission. How does it happen? Although you explained from the very beginning the chain and all of that, but then we have a source.
Yep.
That's where it's being generated. Now, are there particular, say, maybe stations that are used to transmit to different places, or how does it work?
So for transmission, Today, if you install a power generation and you want to connect to the grid, one of the requirements is that you must provide evacuation assets. What we mean by evacuation assets is after you step it up to 330, you must do a station where transmission line can connect to and take it away from you.
Okay.
So your step up, you must provide a transformer, step up transformer, then a gantry where whatever needs to happen there happens. Then transmission will connect. Now we have 330 lines across the nation.
Okay.
If you look at the map, there is a map that shows all that. If you look at the map, there is so much in the south than the north. There is so much in the south because there is so much power plant in the south. So if I have a power plant here, I must step up to 3330. If someone else has a power plant here, he must. If someone else has a power plant here, he must. So at the end of the day, we might end up having so many lines. So there are lines and there are substations. So when 330s travel to a good distance, depending on the planning, all this is not done by, I just want to put a power station here or a transmission station here. No. It is planning. There is a department in TCN and NISO today that sits down to do all the planning. Where should the transmission station where should they be located? What should happen there? There are transmission stations where all that happens is you step down between 330 and 132. There are transmission stations where there is 330 to 132 to 33. Depending on the demand around there, like Lagos, you typically have transmission station that houses the 3 voltages. It will take 330, step it down to 132, then further step it down to 33 and serve the distribution customers. So there must be transmission substation and also transmission lines. And all this planning is done by a department in TCN. So it's not jerry pick. Someone just want to throw it here, or somebody want to please somebody there and just put a transmission line there. No.
Well, I think we'll get proper into the TCN and talk about the major role they play. Okay. But then right now, let's go on a very short break. When we come back, the conversation continues. Please stay with us.
Everybody has a stake in making the world a better place with love and compassion. As we thrive daily, we continue to strive to face the many challenges that faces our Earth, because together we all matter. On one side, we are exploring the captivating stories, the trends, the glamour, while on the other hand, we're looking at the love, the care and compassion from our champions. In our Stars Quiet Cove lies the burning passion for humanity, which is seldom known and unsung to the world. Join me on Famed to look at the flip side of your favorite beyond the regular.
For 2 seasons, Timeline has taken you on a journey of exploring real-life issues and solutions. Well, we are on to season 3 of Timeline, a space where we talk about real issues shaping our world. Here, we sit down with voices that matter, with people who are driving change and making impact. We are talking about more than just problems. We're talking about the attainment of our collective commitment, the global goals, the SDGs, and of course, our community-specific targets. Our conversations aren't just about highlighting problems. They're about finding solutions that truly works, solutions that touches lives and impact the globe. An appraisal of how close we are in meeting our global and community targets. We create rooms for honest, thought-provoking conversations, a ride that you wouldn't want to miss. Well, this is Timeline, where conversations lead to solutions that change lives.
Well, thank you so much for staying tuned. We're still talking about electricity generation, transmission, and distribution. Well, thank you so much for still being here.
Thank you.
Okay, so let's talk about distribution. We've talked generation, we've talked transmission. Let's talk about distribution, and then we'll probably dwell on the regulating body you earlier mentioned. How do what are the things involved? What are the things involved? I know of the fact that we have a grid.
Yeah.
Because almost now and then we hear, oh, the national grid has collapsed. The national grid has collapsed. So tell me about transmission and how it works.
Distribution.
Oh, distribution. I beg your pardon.
All right. Distribution works some way like transmission.
Okay.
So what happens at transmission is just high voltage. At distribution, they want to bring it down to a voltage that customer can use. Okay. So the same way transmission picks it up from generation and drops it at the door of the distribution. Distribution companies also pick it up from transmission and drop it at the door of the customer. So in a distribution sector, you also have, we call it injection station, distribution injection station. Okay. So at that level, they pick the electricity up from as 33 kilovolts. That's 33,000 volts. And they either step it down directly to usable voltage, which is 230 volts to the customer, or they first step it down to 11 kilovolts and now further step it down to 230 kilovolts. So at the distribution, 230 volts, at the distribution level, you will typically have an injection station and then your distribution transformer. Now, your distribution transformer, that's the transformer you see on your streets all that. Yeah. They take the voltage as 11,000 volts and now step it down to 230 volts so that you can use it. So that's what happens at the distribution level. So distribution also does almost the same thing as transmission, but now they do it to customer at a lower voltage, and they are responsible to also drive the commercial.
Oh, interesting. Yeah. So what role do grids play in this?
So we in Nigeria, we call the grid, the only thing we call grid in Nigeria is just the transmission. But the truth is, from 330 when it's been stepped up to 11 where it's been stepped down for customer usage is grid. So even your distribution lines, they are grid. But in Nigeria, we just say national grid. National grid is just transmission lines, right? Okay. But in practice, it's a grid. The entire line is a grid. The only thing that is not grid is that your wire that is connected to the pole. But every other thing from that pole to where it's been generated is grid.
Interesting. Okay, so now let's go back to the TCN you earlier mentioned. Yeah. Of course, you were talking about the fact that you don't just wake up and say maybe having a transmission plant or something. There are people that sit down to plan it and regulate it and all of that. So now, are those people active in Nigeria? Yes, I know the answer would definitely probably be a yes, because we have the TCN. Yeah. But then, do they really do the work of checking and planning? Because sometimes it's bothersome that it's a community that is taking care of its transformer or something. I don't know if that's
distribution. The right. So when for transmission, right? Transmission Company of Nigeria, of course, active. If they are not active, you won't see light in your house. If Transmission Company of Nigeria and Nigeria Independent System Operator today should say they want to back out, they are not doing anything for the next 24 hours, I can bet you the entire country will be in the dark. So as long as you see a light bulb in your house, it means that there is a guy or there are some guys behind the scene that is ensuring that what happens on the grid is balanced. Now, one of the critical role they play, especially NISO, that's Nigeria Independent System Operator. Okay. One of the critical role they play is to balance the supply and the demand. Now, when power plants generate, they must generate in response to the demand. That's what customer want to use per time. It's like a seesaw kind of thing.
Relationship.
When we were kids, and someone will stay on this side, one will stay on that side. If I'm bigger, this guy will go up, right? I will be down. Yeah. And until we balance the load,
Yeah.
we can't have a state of equilibrium. That is what NISO does at every point. The moment one side is beyond the threshold, then what you see is grid collapse. So anytime there is a grid collapse, it simply means that at that instant, the supply is not equal to the demand,
No
or is
balance.
not within the threshold. So what they do is they monitor the frequency and the voltage per time, and also the load and the supply. So there are people that is in a control room that are looking at all these numbers, and they are giving instruction per time to distribution companies to drop load. That means switch off some of the lights because maybe one generation station just went out, or because maybe a transmission station just had developed fault. So they have to immediately balance what is happening. The TCN today, because they all used to be TCN until the unbundling happened, and then we have NISO and then TCN. The TCN are responsible for the maintenance, for the installation of the transmission line. So their work typically is just service provider. They are to pull the line, maintain the line, ensure all those equipment are well maintained so that they can serve us. NISO, on the other hand, look at what is happening on the grid, and they are trying to balance it per time. So NISO TCN is very active. It's a company on its own where day-to-day running of the grid happens, and everything everybody in those two organizations are doing is to ensure that we see this light bulb being on.
Wow, interesting. So that's quite commendable, the way you broke it down. At least if I hear that the national grid, although you've broken that down, collapses, I know that some people are there working because it's definitely come back up. But now let's look at possible technological advancements, right? Now, does this electricity distribution, no, let's start from generation, transmission, and then distribution. Is there a way that maybe the current trends in technology has impacted on its effectiveness?
So definitely, can we do a lot of things better? Absolutely, right? Technology can help us do so much better. Sometimes, I think 2 months ago, thereabouts, NEC, who is the regulator, issued an order that all generation stations must make their generation plants ready for connection. That's SCADA ready. Okay. So SCADA is some sort of supervisory equipment.
Okay.
So that you can supervise and you can control. So you won't need someone to call, or because what typically happens today in terms of balancing the load is you have to make a call and demand that switch off, switch on, ramp down, and all that.
Oh, wow.
So, but technology has advanced. All you need to do is to have sensors, relays, planted everywhere and anywhere that is necessary, and there's someone that is looking at what should happen, and then even those relay and sensor can trigger themselves. We can have that technology embedded. I know TCN is doing a lot to ensure that SCADA come on board. There have been news as per how much progress they've made in installing SCADA on the grid. I hope that will get done in no distant time. But SCADA also is not just useful for transmission, it's also useful for distribution.
Okay.
Because ordinarily, when distribution line goes out on fault, what typically happens today is you see the NEPA guys, let me call them NEPA, whichever distribution company that serves your area, you see them carry ladder and their vehicle, and they are looking for where that fault happened. So because the fault typically, especially on the line, it means that there is a disconnection between the line. So the wire supposed to go straight. Maybe there's a cut. Maybe the wire is resting on a conductor and it's
quite a lot.
It's hitting it. Yeah. So I don't want to use some terms that people will not understand, right?
Get it.
So they look out for those faults. But if IoT sensors and all that is on the line today, somebody can sit down and say, go to so junction, that's where the fault is, and they'll get it done. So technology has advanced a lot. But of course, these technologies are not cheap. Right? And this technology, no matter the investment you make today in that line, must be recovered. Right? And today as a sector, I think we are still battling with huge losses. We are still battling with almost 40% loss, which means that if 100 kilowatt hour of energy is generated, or let me say a watt of 100 naira energy is generated, you will lose almost 40 naira.
Oh, wow.
So what is being recovered is barely 60 naira. So in that case, making all those investments becomes a bit difficult across the value chain, because it is customer that makes the value chain run.
I was going to come there, and I think that's what we pay for, right? The electricity bill.
Yes. But what we pay for is still way subsidized by the government. The subsidy today is almost, I think, 60% thereabout.
That's very correct. When you were talking about the role technology is playing, my mind just went back to, oh, really? So there was someone there at the station who trips it off and turn it on, like, oh, NEPA, and then it's actually someone doing it. So that's quite fascinating.
But sometimes it does itself. That's when there is a fault. It trips itself.
Oh, that when there's a fault. But it normally, if it's working without
fault, and maybe you are on let's say band C, and you're entitled to 12 hours, then they have to do that, switch off and then switch on.
Let's talk about these bands: band A, band B, band C, and I think this falls within the distribution level, right? So now band A gets a certain amount, and then they pay a certain amount. Band B. So can you just break it down for a lot of people who may not really understand what these bands?
So the idea of the band is to try to how will I put it now? Is to try to compensate for alternative source of generation. Okay. So what that is trying to do is, if I'm a band D customer, I'm entitled to about 8 hours. Right, 8 to 11 hours or almost 12 hours in a day. So it means that I will definitely run my generator. Okay. Right? So if I will run my generator, why should I be paying as much as somebody that gets 20 hours in a day and might not run his generator, or is running his generator for barely 4 hours? So the idea is, the more you stay on the grid or get supply from the grid, the more you should pay. Because there is somebody down there that is burning fuel to complement what is not, because we don't have what we generate today is around, now we're hovering 4,008 to 5,003, 5,005 and all that. That is not enough to go around the entire country. So the banding thing came into being to kind of bring equity. Let me put it that way. Yeah, because it's just fair that I'm not getting supply and I'm not paying as much as someone that is getting supply. So that's actually the genesis of band A, B, C, and D, and E, and all that.
So how does the apportioning come? How do you pick areas that have band A or band B, band C, and so forth? So
distribution companies are meant to do that. There are things to look at. Distribution companies, if you want to upgrade a feeder to the next band, one of the requirements is that you must have given those customers that level of supply for 25 consecutive days. Okay. So if a feeder is on band C, typically receiving 12 to 15 hours thereabout, and then you've been able to give them, let's say, 16, 17 hours for good 25 days, then you can say, NEC, I want to upgrade this feeder from band C to band D, because I've been able to provide supply for them consistently for 25 days. Then one of the reasons why all the banding also happens is just in a way to bring efficiency into how distribution company operates. Right? So they want to drive, because if a band C customer is paying way less than band A, it means that your revenue is higher at band A, and then band A is cost reflective. So which means all the costs are recovered, but all others have been subsidized. And you as a disco or distribution company, you will want to move your customers higher, and they don't want you to just arbitrarily move them higher because you just feel like. So you must show workings. You must show that you can do it, because immediately you move them from a lower band to a higher band, they are paying more. So they must see value for the money. So this could also look at the losses around the areas and all that happens in terms of commercial. So they don't look at just technical, they also look at commercial. Because if an area is endemic with losses, that means there are a lot of customers that are stealing. Then if you give them more light, you're only increasing your loss. So they have to look at their commercial books also and be sure that this area, I can't increase it until we clean up that network and reduce the loss. Once we reduce the loss, then we can give them higher supply.
That makes a lot of sense. So it's, before now I was thinking maybe there are urban areas will be band A, then rural areas or less developed. Actually, thank you so much for clearing that. But then before we go quickly, as we're rounding up, what are some key misconceptions? Well, I just shared one of the misconceptions I personally had when it comes to this banding everything, and generally for generation, transmission, and distribution. What are some of the key misconceptions you think people need to be cleared on?
So people think that the government is not doing enough to give them light, or the distribution company does not want to give them light. But it's not true. It's not true, because if I run a business and the business generates losses, I will scale down the business or close shop, right? So I will not close a thriving business. I will put in more money. If I should go to, let me make an example. If I should go to Kano State to sell dog meat, and I go to Cross River State to sell dog meat, my patronage in Cross River will be higher than Kano. In no time, I will close Kano shop and divert all my money to Cross River to increase the volume I'm selling in Cross River. Because typically the environment in Kano doesn't allow eating of dog because of the religion. But there is a part of Nigeria where it's cultural. It's not a big deal, right?
Like where I come from.
Interesting. I never knew, right? It's not a big deal. So I would rather invest more money in that area. And that's what typically happens. So when you see Bande having more supply, or some feeders are upgraded to Bande, it typically means that the customer in that area, they are not stealing. The customers are the bedrock of the functioning of this power sector. If the power sector would change today, it's the customer. I do say it. If you sell the disco we have today, if you like, sell it to 1 million companies, sell it to foreigners, sell it to bring whatever you want to bring. As long as customers' mindset has not been changed, the business will keep being the way it is. Because customers sees we've used power as an amenity for so long that a lot of us grew up and we feel, why should I be paying 100,000 in a month for power?
I was about to say that some people feel it's their...
That's right. It's free. They should not pay.
Right per se, but then it's just some basic amenity.
So it has stopped being amenities the moment privatization happened. The generation has been privatized. The distribution has been privatized. The only value subsector is the transmission. And transmission has not been privatized because it's capital intensive. If transmission today is privatized, our tariff will be only God knows. So that's why if the sector will work, customers should not think Disco doesn't want to give them light or government is not doing enough. No. If every customer today decide to be paying for their bills, or they are vending and they are not bypassing their meter, the sector will improve.
So even with the prepaid meters, people still bypass? Just a quick question.
Yes, people bypass meters. A lot of people bypass meters because by the time they start vending and they realize that I'm vending too much, I'm vending 70K in a month. No, I can't continue like this. Instead of you to scale down your consumption, switch off what you are not using, ration what you are using in your house, they will look for ways to bypass that meter. And whenever you bypass, what you've just done is you've made Disco handicap. And by doing so, you've made the entire sector handicap. We have subsidy being paid by government today because if they pass down the entire costs of electricity today to customer, the level of loss and theft might skyrocket because customers are not ready to pay that level for light.
When you put it that way, I think I totally understand. Thank you so much. You've been able to successfully break this down. Personally, I've gotten understanding, and I'm sure a lot of viewers also will get understanding. Thank you so much for joining us.
Thank you, Blessing.
Well, it's been an amazing episode right here on Untangle. And sure to join us for another insightful conversation next time. I remain your host, Blessing again. Bye for now.